Welcome to Friday afternoon at the Arthur C. Clarke Center for Human Imagination, which is a space in your imagination, because we typically hold our events over in Atkinson Hall or maybe a couple other places, but it's the first time we've been in this neck of the woods. So glad you were able to hunt us down and be here for what seems to be a kind of recurring thing for the Clarke Center to help to engage Sir Roger Penrose in a series of recurring things that we're trying to do that also helps get the Penrose Institute going here. And you know, today, and Sir Roger's talked about a number of different things in his different appearances here. And today it's a cosmological matter that he's discussing. And, you know, what he's done is run the gamut from thinking about issues in cosmology to things in artificial intelligence to things about consciousness. And for me, this is really, you know, such a terrific example that, you know, that we can point to from the Clarke Center's perspective on how the imagination is able to extend our understanding of what we think reality is into territories of the unknown that we then can explore and test and utilize to then kind of reconstruct our view of what the nature of reality is. Because, you know, and I think it also points to that most of what we really know are fragments of this phenomena we call reality, and that it's our sense but we're wired. Our cognition is wired to kind of try to make sense of those fragments, and I think that sense making is also something that I would attribute to the phenomena of the imagination as well. And, you know, and that, you know, kind of comes out of this ability to kind of, you know, anticipate the stuff that might go bump in the night and how we might have to take measures to you know, take guard against that during the day. And here I think what we see is a way in which, at least some of the things that I think about when I think about how Sir Roger's work relates to cosmology is to think about how we take these fragmentary ideas that describe the universe, like general relativity on one hand and quantum mechanics on the other hand, but the way that they connect right now is still something that we largely have to imagine, that then it kind of can guide us to thinking about how we build the knowledge to bring those two things together. And but to further introduce today's program, I'm going to now introduce Dr. Brian Keating here, who's the Associate Director of the Clarke Center and a Professor of Astrophysics here at UCSD.
Well, it's a great pleasure to have Sir Roger Penrose back here for the second time in less than a year. And I'm happy to announce that we could only get him here if we promised to replicate the weather conditions of Oxford, England at this current time. So the weather cooperated with us. Sir Roger was here last in the summer, participating in a program led by Dr. Hameroff, who runs a yearly conference on the science of consciousness, which is a topic that was also engaged with very heartily last night by Sir Roger and members of Brain Corporation, which I love. I like anything that is an anagram of my first name. But the Brain Corporation is striving to make these autonomous objects that follow laws that were first brought to my attention in 1989 when I was in high school by Sir Roger in his epochal book, The Emperor's New Mind. And that really set me on a path of curiosity and discovery and wanting to imitate one, you know, millimagnitude of what Roger's accomplished in his career. He spanned realms from mathematics to physics to cosmology to ontology, philosophy, consciousness. He's as intellectually peripatetic as they come. And he's really a role model that exemplifies what we stand for in the Arthur C. Clarke Center for Human Imagination, which is bridging these interdisciplinary venues from arts to science to medicine, and being able to so astutely walk in all these different fields is just so impressive to me. I'll give you his official bio. He's the Emeritus Professor of Mathematical Institute of the University of Oxford. He's winner of the Copley Medal and the Wolf Prize, which he shared with Stephen Hawking, who went on to some fame as well. He's made all-encompassing predictions, models, theories that have ranged from both things that we formerly thought were forbidden, symmetries in nature that were only recently discovered to have, as I say, forbidden symmetry, five-fold symmetry. And actually, some of Sir Roger's tilings, famous Penrose tilings, will be shown in the $2 billion plus new terminal that's being built now currently for opening. I believe it's part of the Salesforce Tower in San Francisco, and it's going to be covered with Penrose tiling, which is quite fantastic. When Sir Roger was here last time, we interviewed him as part of our podcast, which we call Into the Impossible, based on a phrase from Sir Arthur C. Clarke, that the only way that you can understand what's possible is to go a little bit into the impossible. So I refer you to that podcast, which you can find on the Clarke Center website, imagination.ucsd.edu. And so it's such a treat to have him here. He's able to speak on so many different topics. It's quite astounding to me to be in the presence of such a scholar. So very much looking forward to it. And now please enjoy this lecture by Sir Roger Penrose.
Well, thank you very much, Brian, and also for the earlier introduction. And my apologies for this archaic. I'm afraid I give lectures these days and according to procedure, which is really outdated, and so I annoy people when I go to conferences because they set up all this stuff just for me, and it's very irritating. But so I apologize for having caused all this difficulty. I should explain what I'm going to talk about. What does CCC mean? It's a proposal that I've made some years ago, over a decade ago, I think, on cosmology. The C's stand for conformal cyclic cosmology. I'll explain what the conformal and cyclic are about. I've talked about CCC quite a lot at different places, but talking about dark matter in this context is a recent one. CCC always had something to say about what dark matter is. I should say that people refer to the mysterious things in nature that cosmology has thrown up. One of them is dark energy, and the other is dark matter, which seem to dominate the material in the universe. The dark energy, so-called, is a thing which very much drives the theory that I'm going to talk about, but dark matter is a sort of offshoot of it, which I didn't dare mention much because I thought, well, look, if it tells you what dark matter is, that's too much, and so I better keep quiet about that. But the thing is, I will say what it says about dark matter. That's the point of this talk. But I think I'll start by just giving you a reference. Usually people do this at the end. I thought I'd do this now because this is a paper by colleagues of mine. Two of them are Polish. I call them my Polish colleagues. The paper that they I think submitted for publication about 5 years ago has finally come out just this Monday in the Royal you see it all down there. It just came out on Monday. Anyway, so this theory tells you, I should say the paper is an observational paper, and they do an analysis of the cosmic microwave background. I'll say a bit more about that later. This analysis, the theory makes a certain prediction about that, and they looked for the signals that the theory predicts, and they found a signal which had a 99.2% confidence. Now, finally, this paper, after lots and lots of complaints, every one of which they dealt with, the paper was published, and on the condition that the authors said in their opening sentences that the effect that they see might be a chance effect, which seemed a little strange because it's always when you look for things and you see it's a chance effect. The thing about this is they actually give the probability that it's a chance effect, and the probability, according to them, as accepted in this paper, is that it's 1 in 125. So it means that the theory has a good chance of being correct. I thought I'd start that way because you might otherwise think that everything I'm saying is a load of cobblers, which of course it might be, but at least it has a observational consequence which seems to rely on this theory, and it's very likely right. Okay, well, let me start by showing you what we think the universe is like, quite apart from my theory. This is a space-time picture, so you have to think of time going up the picture. Actually, what did I think of going up? It's still there, never mind. So you have to think of the time as sections through this, and I'm representing these as sections as you go up, so the time progresses. We're somewhere around here, I'm not sure exactly where. You have to think of this as three-dimensional space. I can't draw all the three dimensions, and time is going this way. This is the Big Bang at the bottom, where the universe began, and this at the top is the exponential expansion that was observed and got the Nobel Prize a few years ago, and people call this dark energy. I don't like that term because it's not really energy in any normal sense, and it's not really dark. It's transparent, that's true, but nevertheless that's the term which is given to it. I should explain what this wiggly stuff at the back is. The wiggly stuff at the back is just that I don't want to prejudice the issue as to whether the universe is closed, in which case this would join up at the back, or open, in which case it keeps on going. So it doesn't matter in this scheme. It might be open, it might be closed, either way. Anyway, we have a Big Bang, and then this expansion starts off like that, slows down a bit, and then it starts to accelerate. And this was the effect that was observed recently, and people say it's dark energy. I prefer to call it Einstein's cosmological constant, lambda. Einstein introduced this term into his equations in 1917 for the wrong reason. He wanted a universe that was static, and so he tried to retract it afterwards when it was seen that the universe was actually expanding, saying he'd made a huge blunder because he could have predicted the universe was expanding, and he didn't because he wanted it static. The scheme that I want to tell you has something in common with the idea of a static universe, but it's not static. I say this picture, I'm not monkeying with that. That is what we see. Some people might complain that there is something right at the bottom here, right after the Big Bang, called inflation. Now, I'll say a little bit about inflation, but in order to say what that looks like, I have to bring out my powerful magnifying glass and have a look, and what we will see is something like this. I should say all that stuff is the handle of the magnifying glass. I don't think that's part of the universe. Here we have the initial expansion, which is another one of these exponential, self-similar, that is, it looks like itself on all scales, self-similar expansion. And to say that it's a bit like what the universe is doing on a huge scale, but this is on a very tiny scale originally, and then it expanded like that. Now, this is introduced for various reasons. Many of them don't really work, in my view. One or two of them are genuine reasons that if you don't have another explanation for them, you're in trouble. So bear that in mind. I want to give you something where, you see, people often talk about inflation because the universe is all very uniform, and they wonder why that could be, and inflation is supposed to stretch out. Any wrinkles would kind of get stretched out. That's a bad reason. That's not a good reason. I want to explain a little about why it's a bad reason, but in a moment, not just yet. Let's think about first the universe as we seem to know it, with possibly, you see, the inflation could be in this picture because it would have taken place right inside that little black spot at the bottom, and you wouldn't even know I hadn't drawn it. So it doesn't matter. But I want to do something to this picture to make it a little bit more comprehensible in a sense. You see, this exponential expansion in the future goes on indefinitely, according to the standard picture. But I want to do something to do it, squash it down in a way. I'm going to squash down infinity to make it something you can look at, and I want to stretch out the Big Bang to make that something you can look at. I'll say a little bit more about that in a minute. But in order to do this, to make this picture fit in a little bit better, I'll draw it a bit smaller. That's the same, the left-hand thing is the same picture we had before, but the squashing down of infinity here makes it into a finite boundary, and the stretching out of the Big Bang makes that into a finite boundary. And so these are two mathematical tricks, and the first one is the squashing of infinity, the second one is the squashing of the Big Bang. just to give you an idea of what this stretching of the Big Bang, squashing of infinity. The squashing of infinity is something which many of you have perhaps seen. This is an Escher picture, which is a similar kind of thing to the squashing down of infinity. This is a kind of a universe. It's what's called hyperbolic geometry. Don't worry about that too much. But Escher's drawn these fish, I think they're fish, black ones and white ones. And the point about this picture is infinity, which is around the edge there, is represented as a finite boundary. And Escher has done this cleverly. Well, it's a transformation originally due to Beltrami, an Italian mathematician. And it's what's called conformal. Now, conformal means that you can squash it down as long as the squashing is isotropic. Squash it the same amount that way as you do that way. So in particular, the circles, which are the eyes of the fish, remain circles no matter how close to the boundary you get. So the squashing is this very special kind, which is called conformal, and preserves angles, it preserves small shapes, but the size can be big or small. So bear that in mind, because it's just that kind of thing which I'm going to be doing in my transformations. This one is just like the Escher thing. It's talking about infinity being squashed down into this finite boundary at the end. And this is the opposite, where the Big Bang is stretched out. Now, I should say something about this idea of conformal, because in space-time, what that means is that space and time get squashed by the same amount. And I have a picture here of what we call the light cones, or the null cones in space-time. At any point in space-time, it's space and time together, that means 3 dimensions of space, 1 of time. I can't draw all the space dimensions, so you have to imagine maybe it's 2, just to ease your imagination. But at any point, you have one of these cones, imagined to be there. What these cones tell you is what light would do, the speed of light, it tells you. So if you have a flash there, as time progresses, that flash increases, and that is represented by this cone shape in space-time. Now, the thing is that the conformal transformations leave these cones alone, because they squash the space in by just as much as they squash the time down. And it's rather remarkable how much of physics is insensitive to this squashing and stretching. Now, you see, well, we would know if you stretched space, because physics knows how big things are. But let me say something a bit more about that. This cone represents most of the local geometry of space-time. Einstein's theory requires a thing called the metric. The metric has 10 numbers to define it. You said it has 10 components. So there are 10 numbers to define exactly what the metric is 1 point. And basically 9 of those numbers, well, really it's the 9 independent ratios of those 10 numbers, are defined by and define this cone. So the cone is really given by these 9 numbers. So in a certain sense, the conformal structure is most of the space-time, because it's 9 out of the 10 numbers. Now those 9 numbers define the cone. What does the 10th number, or the scaling, where do you get that from? Well, you get that from clocks. So I'm imagining here some clocks zipping along at different speeds, and they're supposed to be identical clocks, and these surfaces here, these bowl-shaped surfaces, represent where the first tick of those clocks would be, the next is the second tick, the third tick, and you imagine the clock coming in this way, and that would be the ticks represented here. Now the thing is, if you had different clocks, one goes ticked faster than the other, then it would change how these cones are, but how these surfaces, the bowl-shaped surfaces are, but it wouldn't affect the cones. So the cones would be the same irrespective of the clocks. Now you see, one of the remarkable things about physics, which is what Einstein's theory really depends upon, is that space-time has an extremely precise measure of time. And if you've got the time, you've got the space. See, it used to be that the measure of distance was the meter rule in Paris. But the meter rule in Paris is no good now for the kind of precision one needs. But clocks are extraordinarily precise. And you don't need the rulers anymore, because you just say, well, if you know what a clock is, then you talk about, instead of talking about years, you talk about light years. Instead of talking about seconds, you talk about light seconds, and so on. So the speed of light enables you to get from time to space. So you don't need the space if you've got the time measure. Now here at the top, I've got the two most important or most famous equations of 20th century physics. One of those has to be, of course, Einstein's E equals mc squared. The other one is Max Planck's E equals h nu. Nu is the frequency, E is the energy in each case, and Planck's formula is extremely important. It's the basis of quantum mechanics, if you like. And what Einstein's equation tells you is that energy and mass are equivalent, mass and energy are equivalent. What Planck's formula tells you is that frequency and mass are equivalent. You put the two together, and it tells you that mass and frequency are equivalent. Another way of saying that is that if you have a stable, massive particle, so it doesn't decay or something, it's a stable, massive particle, it is a clock of extraordinary precision. It has a well-defined mass, and that mass means that it ticks at a rate which is absolutely very, very extraordinarily precise. And this precision enables you to measure space-time to an extraordinary degree. For example, one of the things in Einstein's theory is that if you go up, or if you have a clock on the ground and another one way up in the air somewhere, that the one on the ground ticks a little more slowly than the one up there. Well, the clocks can be measured so precisely that I had a clock here and a clock here. You could measure the difference between the time rates. So that, and the precision of these clocks really depends on these fundamental equations here, something very fundamental inbuilt into physics. Now I'm going to undermine what I just said, in a sense. When I say that the measure of space and time depends on clocks, if you don't have any mass, if you only have things with no mass, then you just have the cones and you don't have these surfaces in here. You have these 9 numbers, you don't have the 10. And an awful lot of physics doesn't require the mass scale. When I say an awful lot, the most immediate part of physics, which has this property, is the behavior of light, electromagnetism, electricity and magnetism, according to the very famous and very wonderful equations of James Clerk Maxwell, who explained how electricity and magnetism interrelate and propagate through space as waves, and that they propagate with the speed of light. And this was a very remarkable discovery of the 19th century. And so this is all to tell you that these cones that's giving you the speed of light is something inbuilt into nature. But you don't have any mass. The photons, the particles which describe light, if you like, quantum particles, don't have any mass, and therefore they're no good at defining the scale. They're only interested in these 9 numbers. They're interested in the conformal structure, and if the world was constructed entirely out of photons, you just wouldn't be interested in the scale of things. There wouldn't be any meaning to the scale of things. Now, I want to say that a lot of what is going on in physics and what are the important things that I want to talk about are really when the mass goes to 0. So let me say a little bit more about that. But before doing that, let me go to my picture, which I just had, this one here. And I said that you could squash infinity down or you could stretch the Big Bang out. But there's something very different about these two things. If you want to squash down infinity, it's an extremely general thing. The universe doesn't have to be completely uniform. You see all the original cosmological models, and still we work with these, that were introduced by Friedman and Lemaitre and Robertson Walker and various people, assume that the universe is exactly symmetrical, exactly smooth, looks the same in whatever direction you look in. And that's a good approximation. But the universe isn't quite like that. It's got irregularities, and those irregularities might spoil this picture. Well, it doesn't in the future. There is a good theorem due to mathematical physicist Helmut Friedrich, who has shown that as long as you just have things like massless particles like light, photons, and things which don't have any mass, then infinity works just as well, whether it's one of these exact models or not. It doesn't matter how irregular it is. Now, it's a very different story when you go to the Big Bang. The Big Bang is something extraordinarily special. And the fact that you can do this stretching out is a very remarkable fact, and we don't know that you can, if you like, but it's a remarkable fact of the universe that it looks as though you can. And I'll have to say a little bit more about that in a minute. But let me first say that these two things I'm saying, these two tricks, mathematical tricks, are very widely applicable, and there's no problem. I don't think cosmologists would object to my doing these tricks. They're perfectly good tricks, and so I've not said anything particularly outrageous at this point. Now I'm going to say something outrageous. That the universe can be thought of one of these sort of cylinders, but that is just one of a succession of what I'm calling eons. So let me bring this picture back. I haven't done this very well by messing myself up. That's the picture I just showed you. What I'm saying is that this on the left is the sort of standard view of what the universe looks like, Big Bang out to this exponential remote future expansion. This is stretched and squashed, but this stretched out infinity becomes the Big Bang of the next eon. I'm calling that an eon, A-E-O-N, and we had a previous eon, another one after us, and rather than the Big Bang to infinity being a unique event and that's it, I'm saying this is something which continues. There was one before, there was one after, and you might say this is a totally outrageous idea, but I did say that there is good evidence for it, and I gave you this probability of 125 to 1. Let's say there's 125 to 1 that this is the correct picture. Well, that's a little bit outrageous. I'm not sure I quite say it like that, but it is at least some good evidence that it might be true. At least some of the implications of the theory could seem to be true. I'll say a bit about what those are shortly, but that's not the main point of the talk today. So this is stretching out our Big Bang and squashing out in the previous eon's infinity. They fit perfectly. And when I say they fit perfectly, the conformal structure, that is these light cones, will match together. Now, how do I get away with that physically? Well, I get away with it physically near the Big Bang because, well, that's the normal picture of the Big Bang. As you go back into the past, things get hotter and hotter and hotter. That means more and more energy in the individual particles. The energy gets so great that the mass part of that energy becomes totally irrelevant. And those particles behave as though they had no mass. So as far as the physics is concerned near the Big Bang, it's really these massless entities, the conformal structure, which is the important thing. What about the remote future? Well, the remote future, you have all sorts of things happening. Well, perhaps I could take it a little bit out of order. One of the things happening is that we have lots and lots of photons all over the place, and photons are massless. We have lots of things like stars and all that. We have galaxies. And what happens to galaxies? Well, the galaxies that we know about, particularly ours and lots of others, have in their centers an absolutely supermassive black hole. And that black hole will swallow material, get bigger and bigger as time goes on. And what will happen to these black holes eventually? They'll be sitting around. But according to Stephen Hawking, and I'm accepting this, after a huge length of time, those black holes, well, they have a temperature. Now, that temperature is ridiculously small. However, when the universe expands and expands and expands and expands, the universe cools down and gets so cold that those black holes become the hottest things around. And then they start to radiate away their energy, and when they radiate away, they get smaller and smaller and smaller and disappear with a pop. I'm calling it a pop because it's not really very big compared with the sorts of energies we're talking right up to the end. Anyway, they disappear. Now, how long does that take? Well, it depends how big the black hole is. According to the standard calculations, if you take the biggest black holes around, it'll be something like a googol years. That is to say, 1 with 100 zeros years. That's an awful long time. But we're talking about eternity, after all, and eternity is even longer than that. So, what was it Woody Allen said? Eternity is not an awful long time, especially at the end. When you see, this is the black holes. You have to wait around. I call it the boring era, when there's nothing left but black holes. But the very boring era, when they've all evaporated away and there's really nothing left. Practically nothing left except photons. Now, the main radiation out of these black holes will be photons, the starlight, which is still hanging around out there, almost entirely photons. Now, photons have no mass, and so maybe we can get away with the idea that there's nothing around but massless things. Now, that does require a little bit of imagination. In fact, you can't really get rid of all particles this way, such as electrons that be hanging around you. There'll be a lot of them don't fall into black holes, and they have a lot of particles that they might get annihilated with, but they get separated from each other, and they'll be hanging around. So I've introduced a hypothesis. There are not too many hypotheses here, actually, apart from the original one here. Hypothesis that mass, after a very, very long time, I don't know how long time it would take, finally fades out. So even though mass is such a precise thing now, in the long, long time that we have available, infinite time, in fact, this mass will fade away. There are some plausible reasons for this, because I'll just be a little bit technical here. The way that particle physicists start talking about particles, the first thing they say, more or less, is about their mass and spin, and these are things which are called Casimir operators. If you don't know what that means, don't worry. Casimir operators of the Poincare group. If you don't know what that means, don't worry. But what it means is if you have special relativity, then in particular mass is an absolute constant thing. But the thing is, we've got this lambda term in Einstein's equations, and I claim that's what it is that is giving this exponential expansion. And that lambda term means that this Poincare group isn't quite the right group. You should be doing a different group, which is called the de Sitter group. And what turns out is that mass is not a Casimir operator of that, so it doesn't have to be absolutely constant. But the rate at which it would change is very, very slow indeed. It's probably much longer than the current age of the universe. So I would say that is undoubtedly the case. We have no evidences yet for any fade out of mass, but one of the features of this model is that I'm suggesting is that it does fade out in the remote future, and that means that you have the conditions of Helmut-Friedrich's theorem satisfied, and so at both ends it seems a plausible thing. I'd need to talk more about the Big Bang, because I said that's something very special. Now, this is important. Let me say a little bit about entropy. What's entropy? Well, it's more or less, I'm going to be very sort of general, colloquial about it. I'll say entropy is more or less a measure of randomness. It's more technical than that, but a measure of randomness. And there is a thing called the second law of thermodynamics, which says this measure of randomness gets more and more as time increases, the entropy increases, and so things get more and more random. Another way of saying the same thing is that you go back in time, things get less and less random. So as you go back towards the Big Bang, you should be seeing something very unrandom with a very, very low entropy. Well, what's the best evidence we have for the existence of the Big Bang? Well, there's something called the cosmic microwave background. This is radiation coming. It got the Nobel Prize twice, so it's something very important in cosmology, which it is. It's this radiation coming in all directions. It's supposed to be, roughly speaking, the flash of the Big Bang cooled down. It's not quite right. It's really 180,000 more or less years after the Big Bang, but it's pretty well the flash of the Big Bang. That's pretty close to the Big Bang. And that radiation is something we see and is very uniform over the sky. And it has another feature. If you look at its, what's called its spectrum, here we have the frequency in this direction and the intensity in that direction, and we see a curve like this. This is a very early measurement that was the first satellites that went up to look for this cosmic microwave background. This is the Kobe satellite, and they found this very close agreement between the shape of the curve representing these frequencies. These lines, I should say, are error bars. They're about 500 times, just so you could see them, 500 times bigger than they actually are. So these error bars fit this curve to a tremendous precision. And that precision is telling you, what's it telling you? This curve is the famous Planck black body curve. And what's that's an indication of? It's an indication of randomness of maximum entropy. Now, there's something here which seems to me, I call it the mammoth in the room. You see, you go back and back in time, the entropy is going down and down and down and down and down until it reaches a maximum. Now, you don't have to be much of a mathematician to realize there's something funny going on there. Minimum, yes, but a maximum? Well, that's a pretty good piece of evidence that you get this random effect. as this very early indication of the Big Bang. But what it's really telling us, it's not a paradox. It looks like a paradox at first sight. When I say it's the mammoth in the room, it's because although astronomers, cosmologists are well aware of this, they don't try to explain it. Well, they maybe try to introduce inflation, but that doesn't do it, as I'll perhaps indicate in a minute if I've got my slides in the right order. Now, the thing is that this is a very remarkable fact. It's a remarkable fact that you have this. Now, it's not that the entropy was at the maximum. It couldn't have been, because that disagrees with the second law of thermodynamics. It was very low, but it was very low in something you don't see in this curve. What you see in this curve is the result of a sort of equilibrium between matter and radiation. And that's what the Planck curve is telling you. There's an equilibrium of a sort, or maximum entropy state, between matter and radiation. What it does not say is anything about gravity. Now, there is something else that says something about gravity. I should say that the other part about this microwave background is that it's very, very uniform over the sky. You measure the temperature in different directions. You have to correct for the Earth's motion, but once you've corrected for that, because a little hotter the way we're heading, a little colder where we've come from, but if you correct for that, you find that the temperature is to 1 part in 100,000 pretty well constant over the sky. The fact that it's not quite constant is important for lots of kinds of observations. But anyway, this tells you that the universe was extremely uniform all the way around. It was very uniform, and that's telling you in a way that this trick which I'm applying in the past is not such a bad trick, because the irregularities, well, let me show you the picture I was going to show you, which is a picture which is rather, you see, I should confess that I'm not a fan of inflation. I don't think inflation ever took place. So even though it is a standard part of current cosmology, and there are good reasons for it, one of them I shall come to in just a minute, there are good reasons for it. One of those good reasons is, well, one of the reasons often put forward for inflation is not a good reason. And one reason I have in trouble is I can't find the critical slide, which I need in order to show you what I'm talking about. Now, what have I done with it? Excuse me a minute. It's the earliest one I was showing you. Ah, yes, it's here. That's right. Okay. Now, you see, this is a sort of picture of the universe. Now, inflation is supposed to be here, and it's supposed to iron out the universe by this enormous exponential stretching. Now, I'm going to try and tell you that that doesn't really work. It's also something else. Let's suppose that the universe was collapsing. Now, it might have been collapsing. I mean, models certainly can be put forward where collapse. Einstein's equations work just as well as that way as that way. They're independent of the direction of time. But if you had little irregularities here, these little irregularities would form black holes. They'd congeal with each other and form one unholy mess. So the picture, the much more probable picture, would be a thing like that. I hope my slides are working here. A great mess. And you can put inflation, the thing called the inflaton, which is supposed to determine inflation. You can put inflation fields in, and it doesn't make any difference to this picture. They don't really change anything. So there's no reason. Almost all possible universes are like that. In fact, you can even make an estimate of how many are like that as opposed to like that. And you find that the number like this as opposed to this is something like 10 to the power, 124 times as many like this as there are like that. So it's an extraordinary chance event, if it was chance, that it was like that. And this is the sort of thing I said, the mammoth in the room. Cosmologists tend not to worry about that. They just think, well, maybe it was something convenient that maybe inflation could do the rest or something. I don't know. As far as I'm aware, my own scheme is the only one that really tells you that it's got to be like that. The Big Bang doesn't work with its conformal stretching unless it was a very uniform initial state. And that very uniform initial state, I spent a lot of time trying to define what that meant, and I introduced a thing called the Weyl curvature hypothesis. in order to know what that meant, you'd have to know what the Weyl curvature is. My colleague in Oxford, Paul Todd, had a much better way of saying it. And his way of saying it is, roughly speaking, that you can stretch the Big Bang out in the conformal way that I was saying so that this trick works. So it really is telling you. This trick works according to Paul Todd's hypothesis, and that's a way of saying that this universe has this special character, that the gravitational degrees of freedom were wiped out, and the rest of the matter can behave as randomly as it likes. Now, you see, as time goes on, there are little irregularities in the matter, but these clump into, galaxies and stars, and the stars get hot, and the rest of the sky is cold, and you have this hot spot in the sky, and the cold background, and this is what life comes from, and all that sort of stuff. So the reason that we don't have a completely uninteresting maximum entropy, useless universe is because the gravitational degrees of freedom were not excited in the initial state, and as they become slowly excited, then we get all the interesting stuff that we have in the universe, life, and all that kind of thing. So what I'm saying then is that, yes, we've got to explain that. The other theories, as far as I can see, don't explain that. This one does, in the sense that the scheme doesn't work unless you can stretch out the Big Bang to make it smooth. So that's really the idea. Now, I talked about the second law of thermodynamics. Let me say something else about it. You might say, okay, if the entropy is going up and up and up and up, and it's a sensible question, why is the universe, and I'm having trouble finding things here because I put the blame on the small space here, but it's really my fault. Yeah, here we go. Here is the model, conformal cyclic cosmology. There we are. And so I'm saying that the Big Bang was the continuation of an infinite future of the previous eon. Now, what about entropy? Now, you see, surely, if the second law is right, that'll tell us that entropy is going up and up and up and up and up. And how can you have a model like this with the entropy going up and up and up, and how does it make sense? Now, it worried me for a long time when I thought of this model. Let me tell you what I believe is the explanation. Now, there are certain things which I say from time to time which disagree with a lot of what physicists say, and I'm going to say something. Well, I have friends on both sides, and in fact, I have one friend on both sides, and that friend is Stephen Hawking. And let me just say, I'm not sure I can read all this here, but I'll let you read it. But the key thing is, well, first of all, where is most of the entropy in the universe at the moment? It's almost entirely in black holes. You have this formula due to Bekenstein and Hawking, which tells you how much entropy there is in a black hole, and as of now, it's utterly, totally dominated by black holes. The entropy in the universe in black holes utterly swamps everything else. Okay, it may not have been always like that before there were black holes, no, but black holes, the amount of entropy in black holes is absolutely stupendous. So those are the main problem. Now, what happens to black holes? Well, I just said they evaporate away by Hawking evaporation. Now, you say, I've got friends on both sides. What did Hawking originally say? The old Hawking, well, I have to come about old and new, the older, or the young Hawking, I should say. The young Hawking said information is lost in black holes. He made a big point of that. But then later on, he got bullied by, I shouldn't say that. He changed his mind. And he changed his mind and said information is not lost in black holes. Now, you see, most physicists don't like information to be lost because that disagrees with a fundamental principle of quantum mechanics known as unitarity, and say, no, you can't lose information. I don't agree with that because I don't believe that this fundamental principle of quantum mechanics is true. The main reason I don't is that if you make a measurement in quantum mechanics, that violates it already. So that the unitarity principle of quantum mechanics, which tells you information doesn't get lost, is violated already in measurements. Now, of course, quantum people have ways of getting around that, and they talk about many worlds and all that stuff. I'm not going to say that I think there's only one world, and in that one world, you've got to do something about the quantum measurement problem. And what it tells you, to me, is that in a gravitational context, and I don't want to go into all of that, although it comes back again shortly, in the gravitational context, the information, or the degrees of freedom, actually what it is, are destroyed. Well, if you like, the unitarity principle is not necessarily true, so quantum mechanics needs modification, and the modification is already there in measurement, but it is there particularly because of gravity, and what's more gravitational than a black hole? Well, black holes lose information, and if you draw the appropriate diagrams and so on, you can see it's obvious they lose information. How can you possibly not lose information? But I should say this is a minority view. It's a minority view amongst physicists because they don't like to spoil unitarity. But these arguments go on and on and on and on. I think that Hawking was originally right, that the information is lost, and to argue that it comes back in some sense is not correct. That's not, I say, a view that's shared by a lot of other physicists. Nevertheless, I think the reasons are pretty powerful. And the argument here is, it's a little bit tricky. So, you see, I don't want to violate the second law, and I'm not violating the second law, but what I am doing is saying that when these black holes disappear, they swallow degrees of freedom. And these degrees of freedom don't count anymore. So you have a definition, entropy, and that definition depends on the degrees of freedom that you're interested in. When some of them get swallowed up by a black hole and get destroyed, you have to change your mind and say, what I used to call the entropy, that's not so good anymore because they use those degrees of freedom, which aren't any use to us anymore. They've gone. So you redefine your entropy. You renormalize the entropy, and that comes whopping down. Every time you lose a black hole, that entropy that you're interested in is much, much lower. And as far as I can see, that works. I mean, in detail, well, we need to check things. But it does seem to me that when the black holes, when they go one after the other, the useful entropy that you use to define things in the physics that's left there comes down. It never violates the second law of thermodynamics because you've changed the notion of what you mean by entropy as time goes on. But that's a little bit of a tricky one. I thought I'd better say that because perhaps I could have waited till the questions and somebody would ask them one. It's a reasonable question to ask. Okay, now I want to talk about the dark matter and all that, and I'm afraid that I probably haven't got time to say all the things I want to say, but before even saying that, let me just make a little point about the paper that got accepted by the monthly notices of the Royal Astronomical Society. And the prediction that I'd made was that I kept asking myself, what's the most violent thing that could happen in one of these eons? Well, the Big Bang's pretty violent, but next after that. And that might have a chance of creating a signal which would get from one eon to the next. And I thought, well, how about the collision between supermassive black holes? We know from the LIGO observations, these wonderful observations, that black holes of a few, maybe 30 times the mass of the sun have been observed whacking into each other, and they send a signal which is so powerful that they can be observed from a galaxy which is many, 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 many light years away. Now, these are only trivial size, just 20 or 30 times as big as the sun, as more massive as the sun. But what about these supermassive black holes? Our galaxy has a black hole which is about 4 million times the mass of the sun. We are on a collision course with the Andromeda galaxy, which has a much, much bigger black hole. I forget the figures, maybe 20 or 40 times bigger than our one. We will collide after a few thousand million years, not so long really. And then but our galaxies may go through each other and go a few times. I don't know whether the black holes will capture each other the first time or second or the third time, but they will eventually feel each other out, spiral around into each other, and kaboom. Well, a little bit bigger than that, except you won't hear it because it's gravitational waves. And okay, some of these detectors somewhere might detect them, but not us. That'll be a little too late for us. But those gravitational wave signals will reach the crossover surface and get through. Now, it's quite tricky. You have to ask yourself, in what form do they get through? And here's where the equations come in. I think I'll just talk pretty well quickly about the equations without telling you too much about them. But this picture, just to show you there are some equations. I've got some things like this. You see the Weyl curvature, which is this thing with a C. It's the conformal curvature, and that's the thing which measures how curved up a conformal space is, where you don't have a metric. And that measures the intensity of gravity in a certain sense. And that has to go through from one eon to the next in order that it fits properly. But the way that you measure the scale of a gravitational wave is by something almost the same, except that when you scale it with this omega thing, that capital thing there, capital omega, they scale differently. And what that tells you is that the wave scaling, that gravitational signal fades away, and so that you have 0 in the Weyl curvature in the next eon. However, the derivative across the surface has a value that you can measure, and then you look at the equations, and I've got the equations sort of written here so you can see the sort of thing they are. There's only some of them. You look at the equations, and they tell you that this disturbance, which was originally a gravitational one, gets transformed into, well, it's the fourth derivative of a scalar field, which has to be created at the crossover. Now, that's a key thing, that you get this creation of a new material. Now, this is the dark matter, according to the theory. You see, if you write down the equations, you find, and it's not so hard to see this, because if Einstein's equations have got to work right across from one side to the other, when you have the compressed state, you've got to have something which pulls the universe together, whereas on the other side, that's not there. Now, when you match from one side to the other, you have to have this conformal factor, which I call omega, and you change it to its inverse on the other side. I know I'm talking to people who will understand these things and other people who aren't familiar with these ideas, so I just rattle through it a bit. But what you find is this factor here, which initially is introduced in order to be able to write the equations down. So you have the Einstein equations, and you find that they go crazy when you get to the boundary. So in order for them not to go crazy, you introduce as a convenience this omega thing. Now, this omega thing is simply a scale factor. It's just a squash factor. And it doesn't mean anything physically. You can see it does. But then you pretend it does mean something physically, and you say it's got an energy-momentum tensor, which is this thing right here. And then you see Einstein's equations become very easy. They're just this funny thing equals the energy-momentum tensor of mass. Well, that's just a trick of writing things down. But the thing is that when you go from one side to the other, what I call the reciprocal hypothesis is the conformal factor becomes its inverse, its reciprocal on the other side. And that is the trick which makes the whole scheme work. And that trick has the remarkable effect that it changes this omega thing, which is initially not real. It's just a way of writing the Einstein equations with an extra factor so that you can have a system of equations which make mathematical sense. They're what's called conformally invariant. They don't care whether they stretch or not, and so they work right up to the crossover surface. However, on the other side, this thing suddenly becomes something quite different. It becomes an actual field. It behaves like a new field which wasn't there before, and this new field, you need it there to make the equations work. I say this is the initial form of dark matter. So the thing is, it does have a match with what we know about dark matter. It's there, it's the dominant material in the universe in the early days. It's still the dominant material in the universe. It only interacts with things gravitationally because, according to this scheme, it's the sort of form of gravity. It carries over those degrees of freedom which are entirely in gravity. Nothing else makes any impact on it except in a secondary way. It's a gravitational thing. It's sort of a scalar partner to gravity. And that scalar thing is the dark matter. Now, this dark matter does various things in this scheme, which is very important. Now, let me just say what do you expect the mass of it would be. It starts off effectively massless, like everything else, but then it picks up a mass. Now, what can that mass be? It's only gravity we're talking about. What mass is there that's only gravity? The thing which is called the Planck mass. Could be a few factors, pi and 8s and things like that, but never mind about that. Essentially the Planck mass. Now, what is the Planck mass? How big is that? It's about 10 to the minus 5 grams. How big is that in ordinary? Well, I always thought of it as about the mass of a flea or a small flea. I've seen it described more precisely as the mass of the eye of a flea. That doesn't seem very big, something you need a good lens or a microscope to look at the thing. But from a particle physicist's point of view, it's huge. Ordinary particles in the ordinary standard model of particle physics are nothing like it. This is absolutely enormous. Now, I've talked to various people, Jim Peebles, perhaps the most distinguished cosmologist there is around, and Joe Silk, who's also a very distinguished cosmologist, independently asked them, well, what are the limits are there on dark matter, observationally from the cosmological astrophysical point of view? And people said absolutely huge. They could be little tiny neutrino thing like, or they could be the mass of the sun, individual particles. I don't think he thought they were that big. That Planck mass particles are way, way within that huge scale. I asked Joe Silk, and he said, yes, that's very plausible from the observational point of view. Some people don't like it because then they more immediately think of black holes at that scale. And a black hole of that scale, except we don't really know what it would do, the theory would be that it would evaporate away in a tiny fraction of the scale. But there's no reason why it should. It could be a stable particle. So what I say is, it's a stable particle. But it can't be quite stable because we don't want it there by the next eon. It's got to come again. Each time you cross over from eon to eon, you create this new dark matter which wasn't there before. That means it has to decay away between Big Bang and infinity. What's the decay rate? Well, the decay rate would have to be determined by the other thing, which is purely gravitational. That is the lambda term in Einstein's theory, which tells you that the half-life of this thing should be not, well, I estimated it's something like 10 to the 11 years. So that's a bit longer than the age of the universe up to now. It needs to be something like that, if not a bit more, for something which I'll say in a minute. So these dark matter particles, well, since I'm going to talk about them a lot, I've got to give them a name. So I looked up on Google to say, was there a god of darkness? And Google said there wasn't a Greek one, but there was an Egyptian one, if you take Egyptian gods, and he was called Erebos. So I gave a lecture saying I couldn't find anything in the Greek gods. And then I looked back again at Google, and it had changed, and he turned into a Greek god. So I was perfectly happy with that. I prefer him to be a Greek god, I think, because he has more status as a Greek god. But he was the god of darkness, and he's a primordial god, too. That fits in very well, because he came in there before other things. So Erebos is the man, not the man, the god. And so this suggests that these particles should be called eribons. So I'm going to call them eribons. I might have called them eribosons. I tended not to do that because I didn't see they were very, very quantum mechanical. But that was a mistake, perhaps. I'm calling them eribons, though. Now, let me see. I can't read what I said. Anyway, these particles have to be there. They dominate, and they have to decay. They have to be scalar particles because they don't have any spin. Now, here are the eribons, and Planck mass. I think I'm just saying the more of those things I was saying here. But let me say one more thing. I did say that I had trouble with the measurement problem in quantum mechanics and the fact that unitarity doesn't really seem to hold when you have measurements in quantum mechanics. And I have this proposal. There are various other people who have proposals of this nature, that gravity, the interplay between general relativity and quantum mechanics, is what tells you that the quantum state does have this decay. If you have it's Schrodinger's cat. Schrodinger's cat, according to Schrodinger, you could make a cat that was dead and alive. According to Schrodinger's equation, if you follow his equation, the cat would be superposition of being alive and dead. And Schrodinger is more or less saying, look, this is ridiculous. People often say, now, well, you could make a Schrodinger's cat. And Schrodinger said you could. Well, Schrodinger was really pointing out the problems with making a cat that was alive and dead at the same time. And then people say, well, you open the box and somebody looks in it, and immediately when they look in the box, the cat becomes one or the other. That's not what I'm saying. What I say is that it's already that. In Schrodinger's one, you have a vial of poison and a hammer hits it or something. I'm saying as soon as that hammer hits it, crash, it already has become one or the other. Even before that, as the hammer moves, it will become already one or the other. But that's not the conventional view, but it's my view. Now, what about eribon particles? If they have a Planck mass, they will instantaneously, when I say instantaneously, in about 10 to the minus 40, whatever, 43 seconds, I think it is, Planck time, which is instantaneous as far as you and I are concerned. So this means you have these particles which try to spread out as a respectable quantum particle would do, according to the Schrodinger equation, and then wham, they reduce into a particle again. So they behave like classical particles. How do they decay? Well, I worried about this. There's nothing to decay into except gravitons. And then I was talking to Yvette Fuentes, who has ideas about measuring gravitational waves in ways that go beyond LIGO and so on. I have a feeling I've lost something on. Can you hear me, or this thing's come off? Anyway, I was talking to her, and I worried a bit, because if you had a detector which could measure a single graviton, and it had a Planck mass, it would blow the blasted thing to pieces. It wouldn't be any use to have a detector. You'd have to, why I say it would blow it to pieces is because the energy in a Planck mass particle is about a sizable artillery shell. You wouldn't want it going off in this room. It would kill everybody in the room. So that's not a nice thing to try to detect. So I began thinking, well, maybe it's not like that. And after all, if it's a classical particle, it will decay into a classical wave. Now, it's still a quantum mechanical thing, so it should have a frequency, okay, maybe a Planck frequency. But if it's got such a high frequency, it will behave in a rather strange way. Now, just to explain this, I don't have any time left, do I, or do I? Do I have a few minutes? 5, okay, I'll try and do it in 5 minutes. Now, you see, I used to think about these things a lot. What is the effect of a gravitational wave? Well, you see, imagine you've got these two arms going out at right angles, and the wave is coming straight down. What it does, it squashes one arm in and stretches the other, and then it stretches you have this effect which is opposite for the two arms. And that they specifically look for. However, if you have a highly oscillatory wave of that sort, and this is, you can think about these things by thinking of lens optics, and that's the way I used to think about it. You imagine an optical bench, which has a lot of lenses you put like that, and you have positive lenses, and you can put them together and see whether the strength of the lens, the power of the lens is the inverse of its focal length. Now, if you put two lenses close together, the powers add up. But if you pull them apart a bit, then there's a correction term due to the distance between them. Now, suppose we have astigmatic lenses. So this is what gravitational waves are like. They squash in one direction and they stretch in the other. So you have pure astigmatism with no focusing positive or negative. Now, if you have two of these lenses opposite to each other, right up against each other, they will completely cancel. But if you pull them apart, the correction term comes in, and they behave like a positive lens. Now, suppose you have an oscillation between these two things like this, then what you see is the correction term, and that's behaving like a positive lens. And that is the energy content of this gravitational impulsive wave. So if you imagine a highly oscillatory gravitational wave, it behaves like an impulse. So if that wave came down at LIGO, it would squash them both at once. So you wouldn't see them. However, if it came along horizontally along one of the arms, then it would squash one way and not do anything the other way. So you could see them. So they're the kind of thing that I imagine that might even be seen by LIGO or something, but have not been said to be seen, but they would go immediately into the rubbish bin. And I hope they keep all their rubbish bins, because I'm rather saying that the rubbish bin could be important. Now, I have only a couple of things to say here. Now, you see, the Erebon decay is important cosmologically for two reasons. One of them, going back to inflation. What is inflation good for? Now, one of the real things that it's good for is to explain something about the variations in temperature over the sky. There's a remarkable feature that they have, and this is what's called scale invariance. So you look at different scales, and you see the same kind of pattern. And nobody could think of a way of explaining that. And this was the reason, in my view, that inflation didn't die at birth, because it has this exponential self-similar behavior. So if you have a disturbance in that inflationary phase, that will have a scale invariance. And so that's the main good thing about inflation. There are a couple of other good things about correlations between things at distances, which are hard to explain if you don't have something either an inflationary phase or something going on before the Big Bang. Now, I say I don't like inflation. Inflation would ruin the picture. It's not just I don't like it, it would kill the picture. However, if you don't have inflation, you've got to have something else which explains this self-similar behavior. Now, there is something there. I don't have inflation, but I have eons. And I have the eon prior to ours, and I say that that eon, if I go back to this picture here we go. Prior to ours was an exponential expansion. It's not after the Big Bang, it was before the Big Bang. This sort of reflects an earlier idea to do to the physicist Veneziano. I think he had a very great physicist. And this is a similar sort of idea. I'm saying that there was disturbance in the previous eon, and that's what caused this thing, temperature variations in the cosmic background. But what was it? Well, you see, I used to think maybe it was these black hole encounters. Well, Krzysztof Meissner, my Polish colleague, convinced me that didn't work because you get very little uniformity and all sorts of clumpiness and all this. Let's not go into all that. But I was persuaded by him it doesn't work. So you've got to think of something else. So I suggested, how about the decay of dark matter particles? He wasn't so keen when I first told him. We had another talk in Warsaw later, and we worked on it. And he said, yeah, you will get the scale invariance. And you can see on the model that you will get the scale invariance. So what I'm saying is that eribons do that. That's what you're looking at in this temperature scale invariance. Now you see, in this picture, I think you get an idea. Here is the crossover surface, or here it is. And you see here are the eribons in the previous eon coming and hitting us, or hitting our crossover surface and causing this temperature variations, which will be scale invariant. This all depends on the decays not being too early or too late in this, so you have to worry a little bit about that. But then you can see them in the same eon, maybe. And this would be a possible way of seeing effects from different galaxies. You might be able to see the dark matter itself if we could find detectors which were sensitive enough to the sorts of signals that I'm talking about. Or maybe you could see close ones in our own galaxy. These are two quite different possibilities. In our own galaxy, they would look like impulsive effects. Bang, just like that. Maybe they're seeable, maybe they have been seen. The distant galaxies is a subtle thing. And I was a bit worried by this because when you look at the figures, and I have some figures here, so and let me not say too much about them. But I say if you look at the figures, and I was worrying about how many eribons there would be in a galaxy and would there be enough of them for gravitational waves detected to see them, and it got very depressing because you'd need to have a signal. You see, I was thinking about this for a reason, that there was a paper, well, not a paper, it was an archive article, I guess. I'm not sure if it's published or even submitted to a journal, by some Copenhagen physicists, astrophysicists, headed by Andrew Jackson, I think, and they claim that in the LIGO data, the amount of it which has been already released, where you see the signals, which are the gravitational wave signals, and you have two detectors, and there is a certain time lag between where one of them receives than the other one, because the signal has to get hit one first and then the other, and that's perfectly consistent, the sort of time lag you see. But what these people said is that if you look at the noise, you're not looking at the actual signal, but just around the signal, and you see things which are considered to be irrelevant, and you find the same time delay. Now, there's an argument. I'm not saying they're right. I know that other people have repeated it and find the same effect. Maybe that it's not a real effect, it's something spurious. I don't know. But it did, when I first heard about this, I'd just given a talk about these eribons in Vienna, and it started to worry me because I thought, my God, maybe they're seeing eribon signals from the galaxy in which those black holes sit. And there would be other examples. If you take the Andromeda galaxy and see what about the time delay there, do you get a correlation there? That's another galaxy that black holes aren't colliding there, but nevertheless, the signals ought to be there. And then I started to do calculations with figures and all that, and I got a bit depressed by this. And how do you see something which would be just a general whoosh from a galaxy, and how do you know it's this different from another one? Well, it was a curious thing because I had a bit of a correspondence with, what's her name, Sabine Hassenfelder, who makes rude comments about people's theories from time to time. And so she was making a bit of a rude comment about mine, and I had a response. I said, well, look, maybe you see you want to have a random signal that you might be able to tell the time delay from a distant galaxy. And she said, oh, you mean HBT, do you? And I thought, HBT, what that's that? So I went back to, I have no idea, what is HBT? Oh, she said, oh, that's Hambry-Brown twist. Oh, Hambry-Brown twist. That's something I knew about, but what does it mean? It's an effect. It's Hambry-Brown twist were talking about the diameters of stars, and they were looking at photons from different parts of the star. And lots of physicists complained they were using interference effects and that they shouldn't be able to see anything because you can only see interference between particles and themselves, not between other. And they said, no, you see this effect. And eventually it turned out they were right, because particles coming from distant parts of the star are automatically entangled because they are bosons. Now, bosons means that the state of those pairs of particles are already entangled. Now, I don't want to go into the quantum mechanics of what that means, but the quantum physicists here will know what I mean when saying entangled. They're not really independent, even though they're widely separated. And you get a certain clumpiness in the signal due to the fact that these things are automatically entangled with the other particles. Now, there's something very similar happens here, because you've got the error bonds from one part of the galaxy and the other part of the galaxy. You think, what does this one know about that one? Well, they're both error bonds, and error bonds are scalar particles. Even though they reduce themselves to looking like classical particles, they're still bosons. So there will be this interrelation between distant decays, very strange effect, and I haven't thought through enough about this to see whether I believe it. So it's a question mark. I think there's a reasonable chance that it's right, and that reasonable chance would say maybe you can, with a suitable gravitational wave detector, see error bonds from distant galaxies. I hope it's true, because it would be very exciting to see the dark matter directly rather than these indirect ways. It may be that it's nonsense, and the signal would not be nearly intense enough to be able to see it. I think you need Hanbury-Brown twists in order to have a chance of seeing it. Anyway, that's the end of what I want to say. Thank you very much.
I think we'll take just one or two questions. We have some refreshments. They brought in some error bonbons, and we're going to enjoy those. So I'd like to take questions from people under the age of 20 only, asserting my host prerogative. So kids in the audience, you can interact with a very eminent scientist. So if you have any question, remember there are no stupid questions, only stupid questioners. No, I'm just kidding. Please, anybody? All right, I'm going to turn it over to older people's questions, which may be less. Well, now I see who's going to ask a question. I know it's going to be interesting. Dr. David Britt. Oh, yes.
I refuse to grow up.
Yes.
Roger, I was wondering about these things. First off, what fraction of radiation at the end of the Google universe, and I pronounce it Google, not Google, what fraction of the radiation in that future universe would come from the evaporating black holes? Because there's going to be a lot of legacy radiation.
Well, I did wonder about this. You see, although it's ridiculously small, the amount of radiation that comes from a black hole, you have to wait until the temperature of the universe gets lower, and that's a big part of that Google years.
Right.
However, in total, there's quite a lot, you see. There's pretty well the entire mass of that black hole will deposit itself in some way and make some kind of...
And the rest is all stretched out.
Well, it will be very stretched out, but then the universe squashes things down, and so you have to address that question appropriately. But it's an interesting question which I had wondered about, yes.
All right. I'll ask some others later.
Time for one more question. Oh, I think you're going to make me run to the back of the room with a serious cold. There you go. This will be the last question. We don't let the food cool off to absolute zero.
My son Otto is like Stephen Hawking. He can't speak, so he types. But he wanted to know if you believed in global warming.
Yes, certainly.
He's 13. My son's 13, by the way.
Okay, well, I don't know that matters what I say for the answer, because the evidence is very strong, and I certainly believe that it's happening, yes. I see every reason why it should be happening. I mean, should in the bad sense, when one knows we're pumping all these greenhouse gases out into the sky, and we have no way of compensating that, or nothing significant going in the other direction. So yes, I can't see why it's not globally warming, and we see it is. So I'm afraid I'm on the rather depressing side of this argument to say, yes, it's there.
Let's thank Sir Roger again and get the food while it's still warm.